All right, let's get started. Thank you. So my name is Andrew Williams. I work at Google on Privacy Sandbox, and my talk today is an update on HTTP cache partitioning for navigations. All right, so this talk is actually an update from the talk I gave at last BlinkOn. So I'll try to recap the basics so that it makes sense for people that weren't here for that. But the TLDR up front is that we experimented with changes to the HTTP cache key for navigations. This was late last year, and we ultimately shipped a change, which we'll be rolling out in M136 at the end of this month. And so this talk, we'll talk about what we shipped, talk about some of the experiment results, some of the limitations, and possible next steps. All right, so starting at the very beginning though, what is the HTTP cache? So the HTTP cache stores request responses locally for reuse, with the thought that going over the network is more expensive than retrieving something locally from disk. But they can also present cross-site leak attack concerns. So the HTTP cache is partitioned to prevent these types of attacks. And what is a cross-site leak? From the perspective of the HTTP cache, usually attacks involve fetching some cross-site resource and then timing the request to see whether the request was made over the network or was fulfilled from the cache locally. And attackers can use this to know internal state about an attack or about a site that's they're trying to probe information. So this is what the cache partitioning scheme looks like in Chrome for resource loads. These are kind of easier conceptually to think about. And we usually say that the cache is triple keyed, which means that it factors in the top level site, the frame site, and the request URL. So we have a diagram here. So in the top, we have a.com page with image. So this is a page that just fetches an image. The resource load that corresponds from this top level context will have a top level site of a.com, a frame site of a.com, and then of course the request URL. So this is the triple key for that resource load. And then an iframe embedded within that page that fetches a different image. Its triple key will be different because it has the same top level site but a different frame site. And so these keys are conceptually different. And what this does is adds security and privacy, specifically because the frame site prevents a website from learning timing information about requests made from a different site. And then the top level site adds privacy by preventing one origin embedded on a bunch of different sites from being able to share state and communicate potentially through timing information. So this makes sense for resource loads, but what about for navigations? First of all, what is a navigation? A navigation is a request for a document to be displayed in a window or a frame. And in Chrome terminology, there's two types with respect to who initiates the navigation. There's browser-initiated navigations, which are requests that are made from interacting with the browser UI. So things like typing an address in the Omnibox and pressing enter, or clicking a bookmark. And then there's also renderer-initiated navigations. And these are things that result from like interactions with the loaded document or from site behavior, for instance, JavaScript. So things like clicking a link on a page or window.open. And so for navigations, top level site and frame site in the triple key don't really make sense because a document hasn't been loaded yet. So what happens? So for the triple key, the sites are just computed from the URL. And so we have an example here. We have a navigation to a.com/page. The triple key is just a.com to a.com. It's computed from the URL that's being navigated to. And prior to the change that we made in M136, these requests are keyed regardless of who actually initiates the navigation. There's one other thing for navigations. There is an existing security mitigation for certain types of attacks, where for navigations that load a subframe, so that load an iframe document, a Boolean called the isSubframeDocumentResource is set to true and is false otherwise. And this prevents certain types of attacks where an embedded iframe might try to attack the top level that it's embedded in. And that's what you see in the rest of the example here. So we have a middle iframe b.com. If it embeds a.com, the top level site and frame site will be a.com of that innermost iframe, but the is subframe document resource Boolean will be true. So this results in separate cache partitions for the top level site and this embedded frame site. So this model opens up the cache to certain types of attack. And one is that if a user navigates to evil.com, it can perform a navigation to any site that it wants to probe information about, and then learn whether the user has visited that site previously. So this is concerning, but also there's an attack that's worse, and it comes from this observation here. So a navigation will share a cache partition also with resource loads on any given page because of how the triple key is computed for navigations and for resource loads. So what this means is you can actually perform certain types of cross-site leak attacks called cross-site search attacks, where an attacker can probe state from an arbitrary page. And so what these attacks generally look like is an attacker will navigate to a site that conditionally loads some resource. For instance, if the user is logged in, or for instance, if you have like a mail application where you can pass a search query in the URL, and then it loads an image if no results are found. So the attacking site can navigate to this page. It will conditionally load a resource, which will have a triple key just because it's in a top level context of the origin that was visited. But then the attacker can navigate to that resource that was conditionally loaded, and these share a cache key. And so the attacker can use timing to know whether the site conditionally loaded the resource. So again, so this is a cross-site search attack, not great for the web. But in M136, we landed a change to try to mitigate against these attacks. And it's called the is cross-site mainframe navigation Boolean. So a mouthful, kind of a lot packed into one name. But this is true for all render-initiated cross-site top-level navigations, and it's false otherwise. And it's computed by comparing the request initiator site to the URL site. And so what this means is cross-site render-initiated navigations, top-level navigations, don't share a cache partition with browser-initiated navigation, so Omnibox navigations, and it also means that same-site render-initiated navigations and resource loads no longer share a cache partition. So you might be thinking this could be not great for performance because less cache reuse means potentially more network requests and more latency. But in our experiment, we found no statistically significant changes to core web vitals. So this is a really cool finding. And looking back at the attacks, we can see how this mitigates the attacks in some ways. So the initial attack, leaking leaking prior visited sites. So the new Boolean that we've added does prevent leakage from sites that the user have visited from like bookmarks. It doesn't mitigate all types of attacks. So specifically, this Boolean will be set for cross-site navigations from other sites. So one big case where this is not mitigated is, for instance, if a user had visited a site via a search engine, the Boolean won't come into play for that. But it does help in some of the other circumstances. But then the other thing where it's really helpful is in these cross-site search attacks, it changes the key between these two resources, so the attacker can't do the navigation to the resource and count on it sharing a cache key. So this attack is prevented. In our experiment, we did look at other potential solutions, and they had some themes. So one was, could we add the full initiator site into the key? This provides more privacy and security. So I was mentioning our current mitigation doesn't protect user privacy in the case where like a user has visited a site from a search engine that would be considered an existing like cross-site navigation. Since we treat those the same, since we just use a Boolean of true for all cross-site navigations, we kind of have the privacy trade-off there. If we instead incorporate the initiator site, like the full site, into the key, then it prevents that type of attack, but also means there's less reuse of caching, and in theory, there could be performance issues. The other theme of our experimentation was, can we replace the is subframe document resource Boolean? Because one side effect that it has is it means that if you have a same origin iframe on a given page, they can't share any like resources. They're in separate cache partitionings or cache partitions. So the thought was maybe if we could relax this restriction a bit, there'd be performance savings. So these are two other experiment groups that we collected data on. So just for cross-site top-level navigations, use the full initiator site instead of the Boolean. And then also for all cross-site navigations, so even subframe navigations, replace the initiator site, use the initiator site, replacing the is subframe document resource. And then we might have the performance benefits of replacing this existing Boolean with the added privacy and security benefits of using the full initiator site. And our experiment results found no statistically significant changes across any of the groups for both desktop platforms and Android, which is good to see. Looking into it, it might probably have something to do with the fact that mainframe HTML is kind of a low percentage. Well, it's around 1% of what's requested from the HTTP cache. But even within those requests, there were only small changes to the cache utilization between 2 and 4% in the experiment groups. So this tended to be along the lines of, with the Boolean that we ended up launching, that had the least performance impact. With the initiator side, those tended to be more, but still not much of a change. And we also found the mainframe HTML cache utilization is already relatively low. So here's some numbers. And for comparison, we show the numbers for fonts and JavaScript, which are things that are used way more in the HTTP cache. So looking at mainframe HTML, around 4.5% of cache utilization on Windows, and Android, a little bit more, but not significantly more. So trying to think why this might be the case, we did some existing research on existing studies and found the Web Almanac in 2021 published some findings on this, and it kind of confirmed what we were seeing. So they have some charts here. On the left, it shows the prevalence of caching by resource type. And so you can see things like font and CSS and scripts are heavily cached, but HTML less so. So here it was only 76%. And then on the right, they found that when things are cached, for HTML, the time to live that is used, like in the cache control headers, is much smaller for HTML than it is for other types of content. We also have, in our experiment, we found a few other things. On Android, in the groups that incorporated the initiator site into the key, there was a significant reduction in mainframe HTML requests that were eligible for caching. We didn't investigate this too much further, just speculating why this might be the case. On Android, maybe there are contexts where navigations are performed from that have opaque origins, which we don't cover here, but these are things like file URLs and maybe also like Android native schemes or things. If anyone has any ideas on that, it'd be interesting to talk about. But we ultimately decided not to ship those schemes, so didn't investigate too much further. And then I think anyone who's run a Finch experiment in Chrome can attest to is the platform is kind of noisy. We ran into a lot of experiment crosstalk and some challenges there. But so performance was across the board around the same. So why did we choose not to take away the is subframe document resource Boolean and kind of ship something that was less restrictive there? And it turns out that there was another attack scenario which we hadn't considered initially. And this is related to client-side redirectors. This is specifically where a site on a given origin takes a cross-site URL as a parameter and then sets window.location to that URL, so effectively redirecting to a cross-site origin. And since this page is initiating the navigation, this is considered a same-site navigation. And so the is cross-site, Boolean and experiment group initiator sites that we experimented on, these don't really kick in. So timing data can still leak. And from talking with the security teams within Google, this is fairly common for sites with OAuth and login flows. So, yeah, the is subframe document resource doesn't factor in whether a request is cross-site. It's just set for all subframe navigations. So it actually prevents malicious subframes from being attacked by attackers who use client-side redirectors to indirectly leak information about the URLs that they're interested in. So the question arises, is cross-site mainframe navigation Boolean subject to these attacks? And it is, except that it's a little bit better for top-level navigations versus iframes, because for iframes, or for top-level navigations, there are at least some mitigations. So specifically, in theory, you can use the cross-origin open policy same origin header to say that top-level navigations to these client-side redirectors can't happen. And this is something that can't be applied to iframes, since COOP doesn't take effect for iframes. And also, from talking with some of the security folks within Google, there may be an effort in the future where we can ship same origin allow pop-ups, the co-op header as a web default, and this may mitigate the attack, but it's also unclear whether all client-side redirectors can opt into these headers. One possible way to fix the approach, or to fix this attack, would be to make the Boolean that we added more restrictive, specifically moving away from a is cross-site Boolean, but just restricting navigations themselves. So either adding a Boolean that is just for any top-level navigation or for all navigations, replacing the subframe one. But this also isn't a silver bullet, because it may have significant performance penalties for single-page applications, which typically load content through things like fetch and then display them to the user. And so if things are fetching and then also performing navigations, then those will be in separate cache partitions, and this can have significant impacts for usability and performance. So following on to this, maybe it'd be worth having an experiment to gauge the full performance impact of partitioning navigations more broadly. Or also, we haven't found a reason to preclude replacing the Boolean that we launched with the full initiator site, specifically for top-level navigations. So things we are considering. And then I wanted to touch on a few related things which we're thinking about, but haven't made any movements on yet. So one is partitioning the cache by includes credentials. So this would separate requests that are made with and without credentials. And this is something that was actually implemented in Chrome a few years ago, disabled by default, and was never launched. And it has security implications for fetches that specifically request credentials not be sent or be sent. And it also has implications for things like co-op credentialist, which I'm not super familiar with. But there is a document from when this was added, if anyone's interested, but something that we might consider. Also, at last BlinkOn, there was a question about whether service workers might be vulnerable to this type of attack as well. And I think the answer is yes, because service workers can also intercept navigations. It seems like one of the few ways where pages can interact from the perspective of service workers. So if we wanted to mitigate the attack for service workers, It's unclear exactly how we would do it, but it might involve changing, like for instance, the cache storage matches API, which is commonly used for intercepting requests and storing them, and then reusing the responses if one has been stored already. But these types of attacks, my understanding, there was a research paper that was written about this. They're very dependent on the service worker script and caching implementations. So whether a site is vulnerable kind of really depends on what caching they're doing. And the sites that are vulnerable might actually be vulnerable for longer because service workers that cache using cache storage, the information that is cached isn't subject to cache control headers, for instance, at least as of a few years ago. So anyway, this might be something to look at in the future, something interesting. And then one final thing is, while we were implementing this and testing, we found that Chrome's implementation of the history.pushState and history.replaceState APIs, they reset the navigation initiator in certain instances, which is counter to the spec and is something we might want to address. So a scenario where this comes into play with the HTTP cache is where a user performs a cross-site navigation. That page uses push state or replace state, which changes the initiator. The user clicks on another link, so navigates away, but then somehow navigates back. For instance, if that site uses history.back, the load for that page will mistakenly use the wrong initiator, which means it'll be a cache miss from the perspective of which cache partition is used. But outside of that, having the wrong request initiator could have broader implications, so something to think through. So each of these might be something worth exploring in the future and something our team is going to think about. But that's all I had. Did anyone have any questions or feedback?
All right, thank you very much.